Hi, my name is James Patrick Evans, and today I'm going to be presenting our paper, Probabilistic Naming of Functions in Strip Binaries. This is joint work done in collaboration with Lorenzo Cavallaro and Johannes Kinder. The problem we are trying to solve is that reverse engineering is very time-consuming. Usually, if we are debugging a program, we use symbols to identify the names and boundaries of functions and data structures, and use them to relate it back to the source code. When real-world software is packaged for release, symbol information is often stripped to reduce the size of binaries and to impede reverse engineering of commercial or malicious programs. Without symbols, it is very difficult to understand what a region of memory does on a high level. In our work, we want to develop a general approach to labeling functions and suggest informative names to reverse engineer, with the ultimate goal of being able to pre-process a stripped binary and add symbol information back in. Our goal is not exact function identification, but we want to suggest relevant names that apply to previously unseen functions. By the end of this presentation, I'm going to explain to you how we do this using our new tool, Punstrip. In the design of Punstrip, we wanted to build a system that learns how functions and data structures interact with each other. For this, we need a large collection of prior executables with debugging information included, and we use this as our training set. We start with a dataset of ELF binaries that we intend to learn relationships from. For every ELF binary in our training set, we first parse the ELF header and discover the boundaries, size, and names of functions. Next, we disassemble the body of each function into basic blocks and lift each basic block into a higher level intermediate representation called VEX. The VEX intermediate representation abstracts away low-level implementation details of machine code and allows our analysis to be architecture agnostic. We then analyze each function in this intermediate representation and extract a collection of high-level features that help us identify the names of functions. After we have extracted a set of features, we store all of this information in a database for fast access and ease of running experiments. We then train a machine learning model based on our features. We call this model a probabilistic fingerprint as it outputs the probability of each function being labeled as a function name that we see in our training dataset. Secondly, we use features from our analysis to build relationships between individual functions and data. This is used to build a factor graph consisting of functions and their dependent factors over a whole binary. The factor graph and our probabilistic fingerprint are then used to build a general graph-based conditional random field. The conditional random field allows us to learn a set of weights that express the importance of individual relationships in naming functions. Finally, after we have inferred names of each function using our probabilistic graphical model, we rewrite the binary's ELF header and insert entries into its symbol table so that they can be used for debugging purposes. Obviously, the naming of functions in binaries is very subjective, and different programs may use different naming conventions and styles, but we want to be able to measure the similarity between function names. To do this, we evaluate the correctness of our inferred function names versus the ground truth using three methodologies. The first and simplest metric is an exact match after regular expression transformation. The second is a lexical approach based on the similarity between individual words in each name. Thirdly, we build an embedding of function names, which we call simple to vec, that allows us to evaluate the similarity of function names based on how they are used in the binary. Our analysis starts by determining the number and boundaries of functions in each binary. In the unstripped case, such as our training data, this information is provided by the ELF symbol table. However, it may also be provided by an external tool, such as Nucleus or Ghidra. After lifting each basic block into the VEX intermediate representation, we perform a series of static and symbolic analyses. We implement constant propagation, live variable analysis, and taint tracking in the VEX intermediate representation, and use it to extract a large set of features including heap and stack memory accesses, determining the number of local variables, stack and register arguments, and thread local storage accesses. We also track interprocedural relationships such as callers and callees, data accesses, and compute each function's transitive closure under the binary's call graph. After we have extracted a set of features from our analysis, we combine them into a single feature vector for use as input into a machine learning classifier. Scalar and vector typed features are easily combined. Graph-based features such as the interprocedural control flow graph are converted into a vector using graph-to-vec. This vector representation allows us to compare the similarity of different control flow graphs numerically. Binary and dictionary typed features are converted into a vector by counting instances and that they appear over all function names in our training dataset. The resultant vector is very sparse. Therefore, we use incremental principal component analysis and project this vector into a subspace of the most varying components. Then, we feed the reduced feature vector into a Gaussian naive Bayes classifier to predict the probability of a function taking each name. After creating a per function fingerprint, we want to build a graphical model that allows us to learn high-level relationships, and with it, the structure of code. We do this by creating a conditional random field, which models the conditional probability of function names given a set of known information for each binary. It works by building a factor graph, based on relationships between functions and data structures extracted in our analysis stage. Each factor graph represents a factorization of the graphical model for labeling function names in the binary. Unknown function names in Y are separated by known factors in X. In this example, different colors represent different relationships. We build feature functions for data references, calls, callees, and our probabilistic fingerprint over the set of all possible names in our training set. Each feature function has a multiplicative weighting, theta, that we model globally and aim to learn. Our feature functions are discrete and are only non-zero where relationships have been seen in our training set. After constructing a graphical model, we learn the model parameters that maximizes the likelihood of inferring the correct function names. We do this using loopy belief propagation, which propagates beliefs about nodes using messages. We propagate messages from each factor to unknown node, and each unknown node to other factors until we have a solution that stabilizes. This is an approximate inference method, but allows us to handle loops and model large, complex graphical structures. We update the global set of weights using stochastic gradient descent across multiple binaries to arrive at a global solution. After inference, we modify the binary and add symbols for each inferred function name. In evaluating Punstrip, we want to be able to match function names that are similarly worded but use a difference in language. Our first approach is to implement a natural language processing-based similarity score. For example, take the following two function names. Punstrip first uses a series of regular expressions to remove compiler-generated names and common library encodings. Secondly, it expands abbreviations according to a predetermined set of common programming naming conventions to split the function name into a set of labels. This could be FD for file descriptor or DIR for directory. Next, we use the process of word stemming to remove grammatical differences between English language words, such as its tense, to reduce each label to its word stem. Then, we use WordNet to produce a set of synonyms for each label stem. Finally, we derive a similarity score based on matching synonyms of labels between both sets. In that way, we're able to evaluate two similarly named, but albeit different, names used by multiple authors. Our final evaluation metric, called symbol-to-vec, allows us to build a method for comparing the names of functions based on their usage within binaries that doesn't take into account any lexical properties. Symbol-to-vec gives a dense representation of function names based on how they are used in relation to their callers and callees in an executable. If we have the following call graph, we take random walks and produce a series of triplets that correspond to a target function and two context functions corresponding to a callee and caller of the target function. In this case, we use the target function USB init, and our context functions are start USB transfer and USB unlock. We use these triplets to build a neural network with one hidden layer. The neural network has n input neurons and n output neurons, where n is the total number of function names seen in our dataset. The hidden layer has h neurons, such that the h is much less than n, typically 128, where n is of the order of 120,000. We then train the neural network to predict the context functions given a target function name. After training, our dense representation of function names can be read by applying a one-hot encoded vector as input to our model, and reading the values at each of the hidden nodes. This dense representation of function names is a vector space, such that similarly used names appear close together, and dissimilarly used names are far apart. This enables us to find the most similarly used functions by looking at the nearest neighbours in symbol-to-vec. Secondly, we can get a numerical similarity score between any names in this space by taking the cosine distance between each vector. Finally, we prove that our representation holds meaningful analogies between individual function names by comparing it to analogies made by a human analyst. In doing so, we prove that the similarity between function names in this vector space are consistent and relevant as an evaluation metric, where other lexical-based approaches may fail. For example, If we take the vector representation of USB bulk send, subtract the vector representation for send, and add the vector representation for receive, the closest resultant vector in symbol2vec is USB bulk receive. To evaluate Punstrip, we carried out two experiments. The first evaluated how our probabilistic fingerprint identifies functions under different compilation settings and compilers. The second evaluated our probabilistic fingerprint in conjunction with a probabilistic graphical model that learns the structure of code. For our first experiment, we created a dataset of 149 programs compiled with both Clang and GCC for all optimization levels OG to O2. We then trained models using a particular compiler and optimization level, and inferred function names in a different setting. We weren't able to compare against academic tools such as Bingold as they do not release their work, but we provide a comparison against leading industry tools and show that Punstrip is superior. Secondly, we perform a large-scale experiment in which we use all C ELF binaries from the Debian repositories to evaluate the effectiveness of Punstrip's probabilistic structural inference and show that we outperform the leading state-of-the-art research tool. To summarize, we build and release an open-source binary analysis framework specifically designed for identifying and labeling functions in binaries. We build a model for predicting function names based on an analysis on the VEC's intermediate representation. We build a graph-based conditional random field that combines our probabilistic fingerprint with known relationships between code and data to infer the names of functions in strip binaries. Finally, we build a vector embedding of function names called symbol2vec based on the analysis of all C ELF binaries in Debian. That concludes this presentation. If you would like to know more, please read our paper. We also release our source code and models open source, both of which can be found at github.com/Punstrip.